Alrighty, so we are starting a new chapter on reactions. This is really getting us into more engineering style problems where we're going to have some system, maybe a rod or a lever or a frame that's supported. So, obviously when you actually have real world problems, you may have a bridge. The bridge is supported by pillars. Or you may have the frame of a machine and supporting, maybe one side is wheels and the other side is a metal post or something. You'll have some system supported, and there's some number of forces on the system. Maybe the weight of the bridge, maybe the cars that are on the bridge, whatever it is. And obviously, because of those forces, also called loads, the supports will react to those forces. Just like, for instance, when you sit on a chair, the supports of the chair are the legs of the chair. And when you sit, your weight is on the chair, so there's some load on the chair pushing down. And so the supports, the legs, react to that load by pushing back up, making sure you don't fall through. That's called a reaction. And so what we're going to do now is try to calculate what the reactions at the supports are due to the loads on the system. Once we're able to do this, then we can analyze bigger, more major systems, like a bridge or a frame or something, and be able to tell what's happening with the inner workings of the bridge. Maybe it's made of a bunch of metal bars, and I want to make sure that the weight, the load that's on the bridge isn't too much, such that it would, break the bridge, it'll bend or something. In order to do it, I'd have to figure out how much weight is going through each member, and then, because the material of that member support that much weight. That's eventually the goal of this class. Well, the step before doing that is, of course, being able to figure out what happens at the supports, because once we know that, the rest will be easy. So, in order to do this, the first thing we need to know is what are the types of supports we're going to need to know about. In engineering, no matter what the actual shape of the support is, they're classified as one of a set of generalized supports. The first support is a pin support. So you can think of this like the hinges on a door. If you think about the hinges on a door, they're the interlocking kind of circular or cylindrical pieces, and then there's a pin that fits through the center, and what that does is make sure the door can't be pushed or pulled off the hinges. It stays on the hinges, but the door is able to rotate around the hinge. So a pin support is that type of support. The way we draw it, or engineers, the default way of drawing a pin support is like this. So let's say this is the ground, or whatever the external part of the system is, and this is this triangular piece, that's the pin. So you may have, a bar. It's supported over here by this pin. And what it does is it makes sure if I apply forces to this bar, the bar can't move left or right because it's stuck by this pin. It's held in place. It can't move up and down, but I am allowed to swing the bar and rotate it clockwise or counterclockwise around the pin. I just can't push it or pull it in any direction. And so that's the first big thing of noting about the pin support. It says the sum of the forces in X must be 0, and the sum of the forces in Y must be 0. Okay, but you are allowed to have a moment. So you can rotate, but you can't move the bar left or right. You can't move the bar up and down. So that's what a pin support does. That means if it's supported by a pin, there will be a reaction in the x direction. So a reaction in the x direction and a reaction in the y direction. Okay, because think about this drawing over here on the right. If I pull on this bar, pulling it to the right, I know the bar can't move to the right because it's pinned in place. So that means this pin must pull back with a reaction, preventing me from being able to move the bar. So that's the key about a pin support. If you see a pin support in your system, that means there's going to be 2 reactions, one horizontal and one vertical. So we call it X reaction and Y reaction. The next type of support, not pin, is called a roller support. And the way this is drawn is very similar. It's still a triangle, but there's little wheels on the bottom. So you can imagine, let's say we have a bar, and let's say it's supported by a roller. Well, obviously with this, if I try to lift up, I can't lift it up because it's kind of supported by the roller, or more easily seen, if I try to push down on this bar, it's not going to go through the roller. It's stuck. It's in place by this support. However, if I try to pull to the right, because it's on wheels, it's a roller support, this thing can move left and right freely. So what does that tell me? Again, some of the forces in X is equal to 0, and some of the forces in Y is equal to 0. However, if I'm allowed to slide or roll left and right, there must not be a reaction in the X direction. So if I pull to the right on this bar, the thing just moves to the right. No big deal. There's nothing preventing me. So there's no horizontal reaction, but there is a vertical reaction. Okay? So when you see a roller support, what you think of is whichever direction the rollers can roll in, you're going to have a reaction in the opposite direction. So for instance, this one, we have the rollers horizontal, like it's on a flat table. That means in the horizontal direction, you will not have a reaction, but in the vertical direction, you will, because you can't push this thing down through the table. Okay, and of course, it's allowed to rotate as well, just like with the pin support. So a roller support, you only have one reaction, and that's in the perpendicular direction. A pin support, you have 2 reactions, the parallel direction and the perpendicular direction. Finally, the last support is a fixed support. And a fixed support is generally, your bar is just straight up into the ground. There's no little wheel system, there's no triangle, you're just in the ground. And so this is literally, let's say you have a pipe, and a pipe is buried in the surface of the ground. Well, if that's the kind of support we have, then what's going to happen? Well, let's say we try to push to the right on this pole. Well, the support is such that this rod cannot, or this pole cannot move to the right or to the left. It's stuck in place. Well, that means there must be a horizontal reaction. Let's say we try to push down or pull up on the rod. Obviously, it's fixed in place, so it can't move up and down. There must be a vertical reaction. And if we try to push and kind of make this rod want to rotate downwards, clockwise or counterclockwise or something, it's buried into the ground. It doesn't want to rotate either. So there's a third reaction, which is a moment reaction. So a fixed support actually has 3 different reactions you have to keep in mind. Number 1, the parallel direction. In this case, that's the X direction. If I try to push to the right, the support will pull back to the left, preventing the rod from moving. There's a vertical reaction. If I try to push down on this rod into the ground pushes back up, stopping the rod from moving vertically. So there's a Y reaction. And then if I apply a force to try to rotate this rod, the ground pushes back, preventing the rotation. So there's a moment reaction. So those are the 3 types of reactions we're going to have to worry about: a pin, a roller, or a fixed support. Almost all the questions we do are going to be pins and rollers. Every once in a while you may see a fixed support problem, but for the most part we're going to deal with pins and rollers. So now that we know the types of supports, what is it we're actually doing? Let's take this example. Let's say we have a 2x4 or something, some piece of wood, a nice rectangular piece of wood. Let's say this end is supported by a pin, and this end is supported by a roller. Okay, if there's a load acting on this piece of wood at these locations, so let's say from here to here is 2 meters, from here to here is 3 meters, and from here to here is 1 meter. Okay, so it's a 6 meter long piece of wood. 2 meters from the pin is 100 Newton force. 1 meter from the roller on the right side is I guess it's 500 Newton force. What do I want to know? The question says find the reactions at the supports. Okay, so obviously, if this piece of wood is supported like this, and of course when I mean it's supported, I mean it's fixed to the ground with these 2 supports, and the force is being applied to the wood at these locations, the supports are going to do something. One thing I know they're going to do, obviously, is push back up, because if I'm pushing down on the wood, maybe 2 people are standing on this plank of wood. Well, the wood wants to fall down through the ground. Well, the supports are preventing the wood from falling through the ground, so the supports will push back up, preventing the piece of wood from falling. So I know there's at least one reaction, but are there others? How do I solve a problem like this? Well, the first thing you need to know is what types of reactions are possible. And that's what the discussion over here was about. Knowing the types of supports will tell me which types of reactions are possible. So on the left, we have a pin. Pin tells me there can be a horizontal reaction and there can be a vertical reaction. There's 2 reactions for a pin, one horizontal, one vertical, every time. Now, which direction are they? I don't know. It could be left or right, and it could be up or down. Now, what you generally want to do is look at the system and try to guess what you think it would be. For instance, I'm guessing the vertical reaction is up, since the forces are pushing down. But there may be other problems where the reaction is facing downwards. And the good news is, if you don't know, if you can't tell by looking at the picture and you just choose one, well, if you chose it wrong, you're just going to get a negative sign at the end. So that's not going to affect the answer. So even if you always want to guess up every single time and you always want to guess left every single time, that's fine. If it happened to be down instead of up, you'll just get a negative answer. So now you know, oh, instead of up, it was supposed to be down. But it's a good idea, if you could figure out the direction just by looking at the system, to choose the right direction. That way you don't get any negative signs at the end. So I'm going to guess, for the pin, I know there's a horizontal and I know there's a vertical. I'm going to guess the vertical should be up. The horizontal, I don't see any left or right forces, so I'm just going to say it's to the left. Now what about the pin, the roller? The roller will have one reaction, and it's always perpendicular. Well, in this case, the surface is horizontal, so I know the reaction has to be vertical, perpendicular to the surface. So there we go. I could call this R1, and this one over here is R2. So there's 3 possible reactions for this problem. And I want to calculate what are those 3 reactions. All right, well, how can I possibly solve a problem like this? What is my available routine? Well, here you go. You have 3 possible equations you can use. The first equation says, if my system is not supposed to move, this system should be in equilibrium. If that's true, then it means the sum of all the forces in the x direction better be equal to 0. Because if it's not equal to 0, then this piece of wood is moving left and right. But if my system's in equilibrium, my wood cannot be moving left and right, thus all of the x forces better be equal to 0. Also, the same way, all the forces in the y direction better be equal to 0 as well. Obviously, I don't want this piece of wood to be moving up or down. I want it to be stable. And then finally, the last thing is, if this is in equilibrium, then this system cannot be rotating either. And for it to not be rotating, that tells me the sum of the moments better be equal to 0. And so those are my 3 available equations. This is all I'm allowed to use. And I'm supposed to use these 3 equations to find my unknowns. Well, the first thing I'll say is I'm on good footing because I only have 3 unknowns. So I better have 3 equations to use. If I had 4 unknowns, then I'm in a problem because I don't have enough equations. In any problem I give you, there's only possibly going to be 3 unknowns. So if you find a problem and you think it's asking for 4 unknowns, you're doing something wrong. Or it's just an unsolvable problem. Here, this problem has 3 different unknowns, 2 reactions at the pin, 1 reaction at the roller, that's 3, and I have my 3 equations to use. Now let's look at what the 3 equations say. Let's take the first one. The sum of the forces in x better be equal to 0. All right, let's look at all of the x forces. All right, well, I've got minus R1x, okay, minus because it's pointing to the left by my choice. And then any other forces? Nope, no other horizontal forces. Okay, that's all the x forces, set it equal to 0. And I get one of my answers automatically. The reaction in the x direction at the pin is equal to 0. So I already have one of my reactions. The horizontal reaction at the pin is 0. There is no horizontal reaction because there's nothing pushing my block or my piece of wood left or right. All right, what's the next one? Sum of the forces in y better be equal to 0. So let's see. I've got R1y pointing up. Okay, then I've got 100 pointing down, so minus 100. Then I've got 500 pointing down, minus 500. And then I've got R2, y pointing up, so plus him. Those are all the vertical forces in my problem. Set it equal to 0. And now we see I have a problem. There's two unknowns in this equation. I don't know R2y, and I don't know, R1y, and I don't know R2y. So I'm stuck. Let's look at the third equation I'm allowed to use, and that's the sum of the moments. Sum of the moments better be equal to 0. Now, the sum of the moments means for the whole system, no matter where I look, anywhere I try to calculate it, if I add all the moments together, it better be equal to 0. So that tells me I'm allowed to choose any point on this piece of wood I want as the point of rotation. Now, generally speaking, you're going to choose one of the supports. Which support do you want to choose? Because I could either choose the left support over here to be the point of rotation, or I could choose the right support to be the point of rotation. Which one do I want to choose? The rule is this. You could choose any one you want, but in general, you choose the point which has the most unknowns. And if you think about it, the reason is, let me go to a blank sheet of paper. When you're calculating a moment, so let's say I got this problem here. Let's say this is the point of rotation. I have a force, I've got a force, and I've got a force. Okay? And I want to do the moments, or the torque. Remember, torque, or moment, is R cross F, force times distance. Well, all of the forces that are at the point of rotation, the distance is 0. Because the forces are at the point of rotation, so their distance is 0. So all of those forces don't give anything in the moment. The only forces that come into play are the forces that are away from the point of rotation. So, if you choose the point of rotation to be the point that has the most unknowns in it, then all of those unknowns just disappear from your calculation. So that's a good thing. It makes it a lot easier. There's fewer unknowns to worry about. So, with that said, let's look at our example. Well, on the left, I've got 2 reactions, and on the right, I've got 1 reaction. So I'll choose the left, because that has 2 reactions in it. I'll choose the left to be the point of rotation. So if that's the point of rotation, then what do I have? I've got this as my little problem to find the moments. Here we go. Here's the point of rotation. I've got 100 here, 500 here, and I've got a reaction force here called R2y. What do I know? This is 2 meters, 3 meters, 1 meter. So, with that little picture in mind, I want to do the moments. Let's look at the 100 Newton force. That 100 Newton force pushes down, and it makes my system want to go clockwise. For moments, clockwise, we call it negative. So, we have minus the force, 100, times the distance from the point of rotation to the force. So from here to here is 2 meters. So now he's done. The next one, 500 Newton force. That force is down, so making me go clockwise, so he's minus again. The force, 500. The distance from the point of rotation to where this force is, from here to here is 2 plus an extra 3. That makes it a total distance of 5. All right, last, R2y. That force, that's upwards. Upwards makes my wood want to go counterclockwise, which is positive. What's the force? R2y. What's the distance? From the point of rotation to where this reaction is, it's 2 plus 3 is 5, plus an extra 1 is 6. And there we go. So just like we did with the last chapter, we had to calculate the moments. And we saw moment is force times distance. And it's all perpendicular stuff. So here, the forces were vertical, so I wanted the horizontal distance from the point of rotation to the force. The first force is 100 newtons downwards. That force, if I think about it, if I put my finger at the point of rotation and imagine this rod rotating, if I push from the top downwards, it makes the rod want to go clockwise. A clockwise rotation is a negative moment. So use minus the force, 100, times the horizontal distance from the point of rotation to the force, which is 2. The next one, 500, again, clockwise, so negative. The force is 500. The distance is the 2 plus the extra 3 is 5, so 5 is the distance. And then finally, R2y. But anyway, there's our equation. Set it equal to 0. So what do we get? We have minus 200 minus 2500 plus 6 R2y is equal to 0. That tells me R2y is 2700 over 6, which I get my calculator out, and I find 450. Now I have my second reaction. Notice it came out positive, and that's because when I guessed that reaction at the roller would be up, and it is up, thus I got a positive answer. If I guessed that the reaction at the roller would be downwards, then I would have gotten a negative answer here telling me I guessed the wrong way. But anyway, notice when we tried to use the sum of the forces in y as our equation, I had 2 unknowns, so I couldn't do it. But when I tried to use the sum of the moments, because I could take advantage of the point of rotation thing, I only had 1 unknown in there. And this should tell you something. This is a general rule. Every time you go to solve a problem where you need to calculate the reactions, always start with the sum of the moments as your first equation. Because it's almost inevitable that you'll be stuck when you try to do one of the other forces. Sometimes you could get one of them. In this case, we were able to do some of the forces in X. But sometimes you can't. Sometimes, no matter what you do, the force equations will have too many unknowns. But you can always start with the sum of the moments and at least get one answer. So that's a good tip for you to use. For all the problems you're about to do, start with sum of the moments first, get one of the answers, and then you can do the sum of the forces afterwards. Anyway, let me finish up this problem. Now that I have R2y, I could go back to sum of the forces in y and say R1y minus 600 plus 450 is equal to 0. Now I could solve for R1y. R1y is equal to 150. Again, he came out positive because my guess of upwards was correct. And now I have my 3 reactions. At the pin, I had a horizontal reaction of 0, and I had a vertical reaction of 150. At the roller, I have a vertical reaction of 450. And this is basically how all the problems are going to go. Now, you're going to have different systems. Some you might have a square plate. Some you might have some fancy looking bridge. At the end of the day, you're going to have some set of supports with some load of forces on the system. You want to know the reactions at the supports? Look at the types of supports you have. Well, if it's a pin support, then I'm going to have 2 reactions, one vertical, one horizontal. If it's a roller, I'm going to have 1 reaction, perpendicular. If it's a fixed support, then you're only going to have 1 support in the problem, because that gives you all 3 unknowns all at once. And remember, you can only ever have 3 unknowns here. So let's look at one more example before we're done for the day. Let's look at this example here. Let's say we have, black. Let's do this. We'll have a square plate, and we'll have a pin over here, and we'll have a roller over here. I will have a force of 10 there, and a force of 50 here. I will call this point A, B, C, and D, and I'll let this distance here be 2 meters, and this distance here, I'll let it be 3 meters. All right, so here's our system. The question is, find the reactions. Okay, so just like before, the first thing you want to do is, what are the possible reactions that can exist? Well, the pins can have 2. It can have a vertical and it can have a horizontal. So I'll call it AX and I'll call it AY. Now I'm guessing here that the horizontal one will be to the left because I see that there's one horizontal force that's pushing to the right. So my guess is, well, the support has to pull back to prevent the square from moving to the right. So the reaction is probably to the left. Also, I'm guessing that the vertical support, the vertical reaction will be up because there's the 50 Newton force pushing down. So I think likely the reaction will be up. What about at the roller? The roller can have one reaction and it's perpendicular to the surface. The surface here is horizontal, so the reaction must be vertical, and I'll call it dy. Again, I'm guessing he's up as well. And so that's what I want to find. I want to find AX, I want to find AY, and lastly, dy. What do I have? Some of the forces in X, some of the forces in Y, and some of the moments, all equal to 0. Those are my 3 equations. So, first one, as I said, let's start with the moments. Sum of the moments is equal to 0. First question, which point of rotation? Well, the rule is, generally speaking, what you want to do is choose the point which has the most unknowns in it. Well, looking at my picture, point A has 2 reactions, point D only has 1. So I'm going to choose point A to be the point of rotation. So I'm going to say the sum of the moments about point A. All right, so A is the point of rotation. Now, what are all the forces that can give rise to a moment at point A? Well, let's look. There's 3 possible forces. There's the 10, there's the 50, and there's dy. Because the forces at A are at the point of rotation, so they don't count. Well, can the 10 cause a rotation? And the way to think about it is you stick your finger where my blue pivot is. And so pretend like, you've screwed the plate in at that point. When you push where the 10 is, pushing it to the right like that, does that make this square want to rotate about that hinge? Yeah. And the square wants to rotate clockwise because of it. So the 10 will cause a moment. Okay. What about the 50? So if you've bolted in at this blue point at A, and you push down where the 50 is, will that cause this square plate to rotate? No, it won't. If you notice, the 50 is pointing directly to my point of rotation. So that's not doing anything. That's like if here's a bolt, here's my wrench. If I push like this on the wrench, well, that doesn't cause the wrench to rotate. It just pushes downwards. It doesn't do anything for rotation. Same for that 50 Newton force. That 50 is pointing directly to the pivot. Another way of thinking about it is, if I redraw it here, here's the square plate, here's the 50, here's the point of rotation. If I try to do the moment for this problem, remember R cross F, force times distance, what's the force? The force is 50. Now, remember, this is a vertical force. So when I want the distance, I want the perpendicular distance. That means I want the horizontal distance. So if this is the point of rotation, and this is the force here, what's the horizontal distance to that force? Well, it's just 0. There is a vertical distance to the force, but there's not a horizontal distance. Since the horizontal distance is 0, the 50 does not give a moment. So that's two different ways of looking at it. Number one is a conceptual way. If I look at this system, will that force make the system rotate? No, because it's pushing directly on this bolt. That doesn't do anything to make it rotate. The 10 does. The 10 makes this thing want to go clockwise around the bolt. But the 50 does not. So 50 does not give me a moment. What about dy? Well, dy is here. That's a vertical force. If this is the point of rotation, and I'm pulling up right here, then yeah, the plate wants to go counterclockwise. Another way of thinking about it is it's a vertical force, so what's the horizontal distance? Well, there is a horizontal distance of 2. So he will give me a moment. All right, so that's just to see if we can tell which forces give moments. Now I do the equation. Well, I know dy gives me a moment, and I know 10 gives me a moment. 50 does not. So the 10, is that clockwise or counterclockwise? When I push up there, that makes the plate want to go clockwise, so he's minus, the force is 10. And the perpendicular distance, well, the force is a horizontal, so I need a vertical distance from point A to where that force is, and that's 3 meters. Then I've got the 50, which is just 0. And then I've got the dy. So dy, that is that clockwise or counterclockwise. When I push up over here, that makes the plate want to go counterclockwise, so he's positive. What's his force? dy. What's his distance? From the point of rotation to where this force is applied is 2 meters. And there we go. There's my equation. So what do we get? We get 0 equals negative 30 plus 2 dy. Thus, dy is 15. I now know one of my reactions. All right, so one of them's done. Let's go to some of the forces in x. All right, so what are all the x forces? Let's see, I've got 10 to the right. I've got ax to the left, so minus ax. Those are all the horizontal forces, set it equal to 0. So I get ax is equal to 10. Notice he came out positive, so that tells me my guess was correct, and my guess was to the left. So dy is up, ax is to the left. Last one, sum of the forces in y. All right, what are all of my y forces? I've got 50 down, so minus 50. I've got ay up, so plus ay. And I've got dy up, so plus 15, which is dy. Those are all the vertical forces, set it equal to 0. So that tells me ay must be 35. Positive, so my guess was correct. My guess was up. So he's up. And so there you go. This is how you do reactions. Notice it's very easy. 3 basic equations. Sum of the forces in x is equal to 0. Sum of the forces in y is equal to 0. And sum of the moments is equal to 0. Usually where students will have trouble is the moments. But that's why the previous chapter we had a whole chapter on doing moments. And we had practice problems for them. So that we could get good at calculating moments. At the end of the day, it's force times distance. If the force is horizontal, you want the vertical distance. If the force is vertical, you want the horizontal distance. Generally speaking, if the force causes a clockwise rotation, we call it negative. If the force causes a counterclockwise rotation, we call it positive. You always start with the sum of the moments because you will always get an answer. And you have to choose which of the supports do I want to make the point of rotation. And while you can choose any point you want, generally speaking, the easiest is to make the support which has the most unknowns, which means it has the most reactions, make that your point of rotation. So for this problem, the pin support at A had 2 reactions, so we made him the point of rotation. So all the distances were relative to A. And anyway, plugged in all the stuff for the moments about A, and we got one of our reactions. Then we did some of the forces in X, got a reaction, and finally some of the forces in Y. So that's about it for reactions. There's not much to it than this, other than just looking at a whole bunch of systems and practicing them. You have to be able to do this because the next chapter, which is the main chapter, analyzing actual trusses and bridges and things, the first step you do to analyze the system is to calculate the reactions. Once you know the reactions, then you do the analysis afterwards. So this is like step 1 of a 2 to 5 step process. But it's a very critical step. You cannot do the rest of the analysis without this. So you need to practice these. I'm going to post some practice problems, some homework problems on Canvas, and you need to work these out. However, you're going to see they all work out the same way. The only difference is where are the forces located, what are the different distances, but they're all done just like this. It's the sum of the moments, sum of the forces, that's it. So it's just a matter of, do you know when to put it positive, do you know when to put it negative, and can you calculate your moments correctly? If you practice it, you'll have it down in a day or 2. If you don't practice it, then you're going to have trouble with the rest of the semester. So definitely practice. Anyway, I hope this was clear. As I said, I'm going to post the practice problems to Canvas soon. And you can also look forward to another video with solving some more example problems. Just to make sure you're understanding what's going on. So until then, I wish you luck.